let's resume the video, and I've got our CT here and our X sub CT, which is 79.8 ohms. And remember, the next step was calculating current. So if we know how much current's going through each of those capacitors, we can then calculate the voltage drop of either of those capacitors. So we switch pin mode here. Just a moment. I know I swapped everything around. It might freak you out a little bit, but I just like it better over here. So let's do I total is going to equal 10 volts AC. Yeah, we don't have to write AC, but we did anyway, so we shall. And we're going to divide that by 79.8 ohms. So just simple ohms law again. We'll whip out the trusted calculator. And we'll put it where we can see it. And we'll say 10 divided by 79.8 equals. And we've got 125 milliamps, or 0.125 amps if we want to stick with base units. That's our call. We can do either way. So we'll stay with base units. So that equals, if I switch over to pin mode, so go right here, equals 0.125 amps. So we'll stay with the base. And we'll move, whoops, didn't mean to draw the line. We'll move our calculator out of our way. So basically what we've got, if I come back here, is through this we've got current flowing at 0.125 amps. So it's simple as Ohm's law now. So we're looking for C1 is what we're asking for. That says 3 microfarad. So we know the current. We know actually we're going to have to calculate the X of C for that. So had to get our total current anyway, so let's do the X of C just for this guy. So we'll have to apply the that for X of C1 is equal to 1 over 2 times pi times frequency, which is 1,000, and I'm going to have to just kind of write sideways here, times 0.0000003, I believe will be right, but we're going to make sure of that with our handy dandy trusty calculator here. And move this guy a little bit out of the way so we don't have the writing on top. So the first thing we're going to do is verify this. So that's basically 3 divided by 1 million. And that equals, whoops, I did 3 divided by 1,000. Let's try it one more time. 1, 2, 3, 4, 5, 6. That's a million. Should have 5 zeros after the decimal place. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Same thing here. And notice I've got 1,000 here for our frequency, and it's because that's 1 kilohertz. 1 kilohertz is 1,000. So basically, to do that math, 2 times 3.14 times 1,000 times 0.12345 equals, and then reciprocate that. So the X of C1 is, drum roll please, 53.08 if we round off. So X of C1 equals 53.08 ohms. So we know that. We're going to clear our calculator. And the next thing we're going to do is figure out how to get, knowing the resistance, knowing the current, how to get the voltage. Well, voltage is equal to I times R, 53.08, times, and that, of course, that's our resistance, times our current, which is 0.125 amps. And I'll just draw us a little border here so we don't get confused. And that equals, we'll just take this value that's in our calculator, since it's representative of this 53.08, and we'll say times 0.125 equals, that's 6.6 volts. 6.63 volts. So there we go. And if we look at our potential answers, let's make sure that's in there. I'm going to move the calculator over. 6.63 could probably round to 6.7. Got just a little rounding error there, no big deal. And we'll click it, and sure enough, we're right. Now, we'll erase all this, see what NIDA is trying to tell us here. In an RC series circuit, X of C and R cannot be directly added even though both values are measured in ohms. So here is kind of interesting. Once we arrive at an X of C and we've got a resistance, we can't just say, well, the X of C is 1, the resistance is 1. Let's add them together and we've got 2K. That would be too simple. No. There is another formula, so get ready to learn it. So let's take a look. And they're not exactly the same quantity. R and X of C oppose current flow differently. So just like we had in RL circuits, we have an effect with this capacitor in here that changes the way current flows with this RC right here. And they're talking about pure resistive circuits here. In a pure resistive circuit, when the current is 0, no voltage drop develops across the resistor. Pretty obvious because voltage is I times R, so if there is no current, no voltage drop. Pretty simple. Basic math. But as the current increases, a voltage drop is developed across the resistor. So we see the start of our sine wave, and we see the rise of our voltage drop over here. And they're in phase. They will sync together. So when we look at the phase relationship of a purely resistive circuit, we're going to find that E and I are in phase. They're happening at the same time, and that's because resistor doesn't do, for lack of a better descriptor, anything wonky to current. It lets it flow at the same rate. So, however, in a capacitive circuit, current is maximum when the voltage across the capacitor is minimum. They are inversely proportional. Here, prior to, they were directly proportional. But watch what happens here. They are going to be inversely. So as the voltage rises, current falls. Kind of the opposite, in fact, the exact opposite of a resistive circuit. And as voltage decreases, the capacitor discharges and current flow increases in the opposite directions. Capacitor is kind of a delay as far as current flow here. And if you think about that, that makes a little bit of sense, because some of you that's big on car audio, you get these big capacitors that will help give you that extra bass thump. And that's just to kind of supplement the amp there. And that's what those capacitors are doing. They're supplying that extra kick to give you that low bass that vibrates your entire car and makes it sound like it's coming apart into millions of pieces. So voltage and current are not in phase. If we take a look at E and I here, we see that they are out of phase by 90 degrees. So voltage is rising, current is falling. And once we reach the peak of this one, we're starting the negative peak of I. So they're out of phase, 90 degrees. Remember this? Remember the word ICE. Current, which is I, in a capacitive circuit, is before voltage. Current leads voltage. So we'll have current leading voltage. You take a look at that graph, you see that the green line there is leading the voltage, and then as the voltage rises, the green falls. So we have a point where we're more positive here. This is having to rise, and then we start toward the negative side. Alright, so comparison of the resistance and capacitive graphs illustrate why R and X of C cannot be added directly. They oppose current flow at right angles. So this is where it's going to get real interesting, so hang on. We're not creating current by any means. We're just altering the time in which the current flows. So, but something interesting is going to happen with voltage drops here in just a minute. Alright, so if two people push on an object in the same direction in phase, the total force equals the sum of the two forces. So if we're pushing this big refrigerator and two guys get on one side of it, push it exactly the same direction, we're going to get the combined effort of their two forces moving it in that opposite direction from them. However, if the resistor and capacitor oppose current in the same direction, they can be added, but they do not. So they're not like these two forces. They're different than what we're used to seeing. And this kind of gets back to something we've looked at before. So if I'm pushing toward the right, I'm the guy on the left-hand side. I'm this guy right here. If I'm pushing that away, and this guy is pushing this away, we're actually going to move this thing in diagonal, especially if we're pushing with the exact same force. Now, if this guy is pushing twice as hard as this guy, we're going to get more of this direction. So it's all going to depend on who's pushing harder here, but in this case, it's a 90-degree thing. Alright, the combined opposition to current flow from the resistor and capacitor is called the impedance, and the unit of measure is ohms. We've learned that before. Here it is again in RC circuits. And here is the formula for total impedance. ZT is equal to R squared plus XC squared, and the square root of that value is what gives us the impedance of that circuit. So we've got an example here, and I'm sure we're about to work it all night, and then we'll work some of our own problems here. So the very first thing they're doing, bear in mind we don't have to solve for C total because there's only one C. We don't have to solve for R total because there's only one R in this example. So we can just apply both of those values. So if we come in here and take a look, we're putting R1 in this place. We're putting C1 there, and it's already calculated the X of C. So it's already given us that. It's not giving us the microfarad or the farad value of C1. It's giving us the X of C1. So that's already been done for us. So we didn't see a step here, but that's fine. So then we're squaring the 30. We're adding that to the square of 40. We're combining those values, and we're getting the square root of that. So in this case, 50 ohms is our resultant. So that's pretty simple, hopefully. Just got to make sure we know what we're seeking. And then to get current, same thing. Take total voltage, 100 volts AC, divide it by 50 ohms, which is ZT. Current's going to be 2 amps. So nothing hard about that by any means. Once total current is determined, we can calculate voltage drops based on these X of C1 and R1. And here's where it gets kind of fun. Looks like we're creating something here because we were kind of used to in past times being able to add up these values and get the total applied. But look, we got 60 on R1, 80 on C1. Add those two, you get 140. And you think, hey, how can that be? We have 100 volts. How can we be 80 and 60 giving us 140? Well, remember, it's lagging. Those two combined are not the sum of this. They're greater than that because some of the same current is lagging because of this capacitor. So we didn't create anything there. We just paused it for a minute. Really counted it twice part of the way is the better way of thinking it. So it's just because of that lag. So, and that's what it's telling us here. We can't add them together here. And we'll get to this slide in a minute. We're about to run out of time again. This goes by quick when you're trying to explain these things, so we'll resume right here on the next slide.